So we start again at the point we left. We have been asking questions as to why should there be magnetic order, long range magnetic order, and what sets its scale of the say transition temperature. So that means that we are basically asking the question because starting from the microscopic interactions in the system and the quantum mechanical processes that go on when electrons or moments when ions with moments come close together and their electrons interact, and then there is an overlap of wave function, and then can we find out a scale of temperature or interaction which distinguishes or selects out one magnetic state from the other. For example, from parallel spin arrangement to anti-parallel spin arrangements. So, this is the question that we are asking, and the second question is what is the scale of that energy. And what we found out was that dipole interaction, which is a very common interaction amongst two moments anywhere, does not do the job, because it is exceedingly small between even two atoms which are separated by say even 2 angstrom, 2.5 angstrom is exceedingly small. It is about 1 degree Kelvin. Whereas the insulating magnets where the moments are fixed at sites and they interact with each other, the scale of temperature which is defined by either the ferromagnetic transition temperature or the antiferromagnetic Néel temperature, which is basically both are ordering temperature. That scale is between say 100 to few hundred, and for certain materials like these are iron, cobalt, nickel for example, it is very high. Of course, they are not insulators, so their magnetism is somewhat different, although the scale that we are after is not electron volt, which is the Fermi energy scale, which is like 10,000 degree, 20,000 degree, 30,000 degree. So, that is a huge scale, that is not what we are after. So, we have to generate a scale which is around 100 degree to 500 degree or 1000 degree. So, that is one thing, and that energy, that scale, that interaction whose scale is that, should also distinguish between spin states, the arrangements of spins, as I said in the beginning. And we found out that just by doing a quantum mechanical treatment of two electrons when they come close by, or two atoms when they come close by, their electrons wave functions overlap, and that requires to be antisymmetrized, and that process, that quantum mechanical process gives rise to a energy which is a separation between two electronic energy scales E s and E t, and that separation is of the order of the scale that we are asking for, and that is given, that is what we defined as to be J. So, that J is a difference between two electronic energy scales. So, it is a small scale, and it is also not too small that we got from dipole interaction. And then we could write a spin Hamiltonian which is given here, which is say minus j s 1 dot s 2 between two spins. In that case, this Hamiltonian, as you can see, distinguishes between two spins parallel or two spins antiparallel depending on the sign of j. Okay. So, the purpose we started purpose with which we started the calculations is more or less served. Now, we got a Hamiltonian, that Hamiltonian has a scale which is in the right ballpark of energies, and of course, that Hamiltonian can distinguish between states of different spins. Now, we can do whatever we normally do with such Hamiltonians. These we can do ground state, study ground state properties, we can study finite temperature properties, ground state and excited state, all that are now available to us, provided we can of course solve these problems or do some approximation to get a solution. So, the main task now is to look at this Hamiltonian or its different versions, because this J can be this is just between two spins, and here for example, in Heisenberg model we have taken long spin interaction between sites I and J, which could be far apart. In common practice, most of the magnets that we study, this Jij falls off very fast. It is small, smaller as you go along in number of sites. So, typically one keeps 1 or 2 or maximum 3 nearest neighbors for Jij. In the extreme case, of course, the nearest neighbor Heisenberg model, where Jij is 0 beyond nearest neighbor, is the most standard model that one studies. It is one of the models which is a celebrated model for spin systems. So, that input has to come from the experimental situation, and as I said, the magnetic structure is also determined experimentally, which is mostly neutron scattering experiments. So, given those inputs, one can start working with this Hamiltonian and try to fit the experimental results. The excitation spectrum can also be obtained from the neutron scattering experiments. That is an inelastic neutron scattering, and that experiment is a very important experiment that tells us what are the excitations of these of the ground state of a magnetic system. So, all these can be tackled starting from a Hamiltonian, which we have written down here. It is called the Heisenberg Hamiltonian. Its different versions, different dimensions, different incarnations are studied in most of the spin systems. J is called the exchange interaction. Okay, so there are some small technical issues, where if you make Ij unrestricted sum, then you have to you can take it out and then put a 2 here. This is the summation I greater than j is it takes care of the double counting of each bonds where Jij is defined. Then you put this 2 to match with this Hamiltonian. Okay, so those are small technical issues that are not very relevant, because once you start with a model, you know what model you have started, what are your conventions, what are your Jijs, and then you just continue. Then what we discussed was that there are these exchanges, which is what we are studying, can be of various types. One is that there is a direct exchange, where the ions containing the moments sit next to each other, but there is also a possibility that there is a non-magnetic ion that separates the two two moment carrying ions in a solid. And the second case B gives a very famous exchange called super exchange, depending on the angle between this the intervening one and this one. So, here for example, it is a straight line. So, the angles are 180 degree, but if the left atom is put at the top of this middle atom, then the angle will be this one. So, it will be 90 degree. So, depending on the angle, the super exchange sign often changes, and so these are these are issues that one deals with when one does the calculation in a real system. But as of now, I am just telling you that there are different kinds of exchanges possible. You have this direct exchange, you have the indirect exchange, and there is and this is the super exchange, and then there is an indirect exchange. and that indirect exchange is where say a deep lying 4f state is far separated. Ion carrying a deep lying 4f state with a moment is separated from another which is also carrying a moment, but they are not close by, but there is a conduction band available. So, this moment polarizes the conduction band locally, and that polarization is carried through to the other ion carrying the moment, and so therefore, these two moments can actually interact, can talk to each other via this conduction band. Okay. So, that is there is an indirect exchange, that is a very famous exchange mechanism called RKKY. We will if time permits, we will discuss. Now, direct exchange, as we said, we have studied in case of hydrogen molecule, formation of hydrogen molecule, where we had two electrons forming a singlet and they go to the bonding orbital. So, this is for example a spin 0 state. So, the interaction, the exchange interaction is such that it selects out the spin singlet state as the lower energy state. As I said, there is this super exchange which normally happens, for example, in manganese manganites and manganese oxide and so on, and this super exchange is the other oxides also, copper cuprate, copper oxide, lanthanum copper oxide for example, and so on. And this is a situation where an Mn atom, for example, which carries the moment, does not see the next Mn atom as a neighbor. There is an intervening oxygen ion O2 minus, and that O2 minus has a field shell. And then we actually showed how the antiferromagnetic configuration in this case leads to more delocalization energy than this one. So, this state, antiferromagnetic state, is has a lower energy because it allows the electrons to move about. So, the delocalization is allowed here, whereas here in the ferromagnetic configuration the extent of delocalization is far less compared to this one. So, therefore, the antiferromagnetic state is favored, it has a lower energy. Okay. Of course, then we also, as I mentioned, there is this indirect exchange in that happens in metals, where there are impurities with spins sitting. Not I mean, impurity, by impurity one means that these atoms with moments or ions with moments are separated, far separated from each other. They are not as dense as the atoms that carry the conduction electron. So, so in this or the moments, I mean, it can happen that the atoms are, the ions are next to each other, but the moment carrying orbitals are deep lying orbitals. So, they do not see each other even if the ions are nearest neighbors. So, that can happen in rare earth systems, where the 4f level carries the moment, whereas the conduction band is comes from different orbitals, and these electrons move about freely. So, it is a metal, but every ion has a deep lying state which has a moment, which is an unfilled shell. So, that is a situation that arises in certain rare earth materials, and in these cases what can happen is that these moments that are, say, deep lying orbitals, they polarize the conduction band locally, and that polarization then moves about. It just, the conduction bands go and just they carry that information to the next ion carrying that moment and carrying a moment, and then this kind of a situation where the so there is so there is, for example, a moment sitting here, there is a conduction band. So, this moment, for example, polarizes this conduction band locally into this direction, for example, and that information comes here to the other spin, and this spin has an exchange interaction with these conduction spins. So, this is for example, a large spin, and this they can now this conduction electron spin can align this spin in a particular direction, and that interaction of course is has a oscillatory behavior depending on the distance r between these two ions. That was figured out by Ruderman, Kittel, Kasua and Yoshida, and so this interaction is named after their surnames. This is called JRKKY, okay, and it is proportional to cosine 2 kF. Kf is the Fermi momentum into r divided by r cube. Okay. So, Fermi momentum of the conduction electrons. So, now you can see that since cosine function oscillates, this will also oscillate. So, this will also oscillate, right, and so depending on the distance between the ions, if one ion is at 0, the other ion is here, then the interaction is J is positive, whereas if one ion is here, the other ion is here, then the interaction is negative. So, it can oscillate depending on where the other ion is with respect to one ion, the distance between them. You can have either a ferromagnetic interaction or an antiferromagnetic interaction, and this is a very interesting situation which is actually practically used in materials when you design materials. So, you choose your distances suitably as you want and change the sign of J by manipulating the distance between moment carrying atoms in a metallic host. So, that is one very important interaction, but we will not discuss it beyond this point because that treatment is way beyond our scope. Okay. So, this is a very interesting mechanism of exchange, is called double exchange. So, what we are doing now is just showing you how many different ways exchange can appear in a system, right. And so, we have discussed direct exchange, super exchange, this is indirect exchange, RKKY, and now we have I am going to discuss something called double exchange. Okay. So, let me just show you what it is. This is a situation which happens in, for example, LaMnO3 when you dope it with strontium or something, then Mn has a mixed valence. So, Mn can be in +3 or +4, these two valence states, and the corresponding electronic structure atomic inside the ion, the electronic structure is such that the 3D level it has 5 levels which are whose degeneracy is lifted, and 3 levels are below and 2 are above. So, suppose you have 2 such manganese ions sitting next to each other. If it is in 3 plus state, then it will have moments. So, Hund's rule applies and moments will be like this. If it is 4 plus, then one more electron has to go away, and so it is in this configuration, for example. Now, these spins, suppose this is one Mn and it is the next Mn next to it in the solid. In these two cases, there is no electron here. So, this electron can move, the top electron can move here. So, that is being shown here, this Mn3 plus this electron can move here. Now, look at the configuration of these 3 spins below. These 3 spins here on one atom, on this atom and this atom are now aligned. So, this is a ferromagnetic arrangement of spins. of this core, these are called core spins. These spins do not move, they are stuck to the atom, to the ion. The one that can move is this one. Okay. So, in that case this can now move here, and everything is fine, because these are parallel with it, this is parallel with this one. So, Hund's rule is satisfied, Hund's energy is satisfied. But now so this is allowed, that means there is a finite matrix element between these two states. So, this matrix element is psi 1, this state we call psi 1 and this state we call psi 2, and then so the state that this is the psi 1, where both of them are ferromagnetically aligned, and the psi 2 is, and the top electron is in this atom. This psi 2 state is where this is same, but the top electron has moved to the other one. So, that is psi 2 for example, and there is a matrix element therefore between psi 1 and psi 2 of the Hamiltonian. So, Hamiltonian has a matrix element, finite matrix element between these two states. That means, which basically means that an electron can move from one to the other. Whereas, in this case the arrangement is antiferromagnetic. The core spins, which are these spins, which are not moving, these 3 spins at the lower level, they are not moving, and they are not moving, and they are antiferromagnetically aligned. And this in this case you can see that this top spin, if I want to move this electron to the next site, which is this red dashed arrow, then you can move, of course you can bring it here, but look, this is anti-parallel to the spins at the bottom 3 levels, the localized spins. That means the Hund's rule is not satisfied, you are going to pay a lot of energy, and the Hund's rule, the energy corresponding to that J sub h, which is called the Hund's energy, it is Hund's rule, this is the Hund's energy. So, Hund's exchange between this electron, this and that, is now dissatisfied, I mean they are not satisfied. So, the electron remains, the system now becomes dissatisfied, and it costs a lot of energy, and that is the situation which is not tenable, the system will not do it. So, that means if I take J h to be very very large, going to infinity limit for example, then this is not even allowed, I mean this costs infinite energy. Of course, quantum mechanically there are always these virtual transitions, but they will cost in very very large energy. So, therefore, this matrix element in this case will be exceedingly small. So, that means in the ferromagnetic configuration, the electron can be delocalized and you gain the energy, delocalization energy again, whereas if you have an antiferromagnetic configuration of the core spins, then you cannot have this delocalization energy, it will cost you a lot of energy to move, and therefore, this state has a much higher energy than this one, and this is the configuration that will be preferred by the system. So, look at this is a motion of an electron under the influence of an Hund's exchange, Hund's rule basically, and that drives an electron, a system from an antiferromagnet to a ferromagnetic configuration, that chooses the ferromagnetic configuration from an antiferromagnetic configuration. So, the spin selectivity, that means the spin order, is dictated by the motion of the electrons. That is exactly what happened in super exchange also, but here this exchange gives rise to a ferromagnetic configuration as opposed to the super exchange, and the super exchange is in an insulating system. Here this leads to metallicity of the electrons of the system. So, this leads to a metallic configuration, a ferromagnetic metallic system. So, this was first proposed by Zener, the famous person whose name is associated with Zener diode, and this one is called the double exchange. So, for historical reasons I will not get into that, but this leads to double exchange leads to a ferromagnetic metallic state. So, this is an interesting. So, as you can see that there are just simple electronic processes obeying quantum mechanics can lead to various different exchange interaction between the so, for example, now I can think of a Hamiltonian where I will write the core spins as S1 and S2, and I know that it prefers a ferromagnetic configuration. So, in this case my J is so J will be greater than 0. So, both the spins are up. The S1 and S2 are these 3 spins, these are 3 by 2, half plus half plus half. So, that is that is a model I can now write for the spins between the spins of the 2 manganese ions in say LaMNO3, doped LaMNO3. So, that is a beautiful example of how quantum mechanics plus microscopic descriptions lead to different kinds of interactions between different kinds of spin-spin interaction driven by the motion of electrons, their delocalization and so on in real systems. What we will do now is to now start from the Heisenberg model and try to discuss how one goes about solving such models in some extreme cases, very simple cases. Heisenberg model is very difficult to solve, and it has not been solved yet except for some very special cases in some lower dimensions. So, what I will do is that I will show you how that this model is used and how one solves or makes approximations on such models to get physically relevant quantities.